Hello, everyone. My name is Emily Caravallo, and today I'll be presenting my final project for computer methods and industrial engineering. The topic is oh, the topic is based on a NERIS 2022 paper titled Using Natural Language and Program Abstractions to Instill Human Inductive Biases in machines. So humans can learn new tasks very quickly, thanks to something called inductive biases, which are like mental shortcuts to recognize shapes and patterns. This paper explores how machines can learn in a more human-like way, and author trained AI agents using both natural languages, description, and abstract programs. These abstract inputs help the AI behave more like humans, especially when compared to simple and less meaningful training methods. All right. In real life decisions are often made with incomplete information. This paper introduced a method called induced empirical minimization that helps machine make a smart decision um, using context like weather or traffic, even if the situation wasn't seen before. This is especially useful for transportation company like Uber or Lyft, which need to recommend the best route under different conditions. All right, to understand better these concepts, let's take a look at the difference between AI agents and humans based on the paper, of course. First, AI learns through trial and errors and often picks up surface level patterns, and it struggles with abstract reasoning and initially perform better on machines that generate tasks, but worse on tasks designed by humans. And on the other side, human are naturally good at understanding abstract rules and can quickly describe text using shapes, patterns, or logic. They also perform better on tasks and follow simple and meaningful rules. Knowing that, you may wonder what is empirical risk minimization. So basically, it is a learning method where we train a model using past data instead of needing full information about every option. The model looks at the work before in similar situation. For example, it might learn that traffic is worse when it rains and use that data to make future route suggestions. I also added a formula that represents the empirical risk, which is the average loss over the a training data set. It is written as L of theta, where theta are the parameter of our model. The sums runs from I equals 1 to n, and where n is the number of the training examples. For example, we compute the loss determined by L or loss function between the predicted output and the true label. On the second part of the equation, the predicted output is written more explicitly um, as g sub theta of xi, showing the prediction come from a model function g applied to input xi using parameter theta. So basically, in simple terms, this formula calculates the average difference between the model predictions and the actual value in the training in the training set. Minimizing the this average loss, we can help the model learn better from the data. This study has important real world implication. If machine can be trained using human-like abstractions through language and code, they can generalize better. So here's a practical example using Gurobi, a transportation company like Uber or Lyft. Um, Wants to find the best route based on time, cost, and weather by using optimization and adjusting a value called alpha. They can decide whether a speed or cost is more important at the given time. This approach minimizes the score as much as possible to have the best possible outcome based on the current weather conditions. In this model, we have three routes, A, B, and C. Each one has different time and cost value depending on the weather. The parameter alpha helps balance the importance of the time versus cost. So when alpha is zero, we care only about time. And as alpha increases, cost becomes more important. So on the right side, you can see the code which I define the times based on the weather, the root cause, and also the loop over the weather and alpha, and the loop to stop Gorobi to obtain a cleaner output. Um, Here you can see the constraints and the objective function, as well as I how I set them up in the code, as you can see on the left side. Well, here we have the result after running the code. On sunny days, route A is the best when we care mostly about time. But as alpha increases, the model start to prefer route B, which is cheaper. As you can see, on rainy days, route B is always preferred as it combines both good time and low cost. This shows how context and priority affect optimization's outcomes. In conclusion, this paper highlights how language and program abstraction help AI learn in a more human-like way. By training machines using these human tools, we can make them smarter and more aligned with how people think. Thank you so much for listening.